Hey everyone, today we're going to talk about RedBlackTrees and my map class. So last week we talked about the HashMap class, so I thought this week would be a good idea to talk about my standard map class. Right, so it could all go terribly tonight because it's it's a number of years since I actually wrote this code, and I've probably forgotten a lot of it. And also I'm in the middle of a juice fast, so I've had a frantic day of coding and I've probably used up all my blood sugar in the brain, so forgive me if I'm a bit slow tonight, but hopefully it'll go okay. So where should we start? Hi there. So yeah, as always, ask me questions as we go and I'll do my best to answer. So when I decided to write my map class, it's not something I'd ever done, strangely enough, because usually, I did computer science at university, and usually that's a pretty standard thing one would do. You would learn the algorithm. But maybe I did and I've just totally forgotten, but I don't remember doing it. So I decided a few years back to take a few days out and just learn it, watch some videos online, and then code it up, obviously. And this stream is not going to be about all the messy details of how you actually code the algorithm or how the algorithm works, because there are literally thousands on YouTube and papers on everything. There are so many really good videos on how to do this. So I'm not going to do that. I'm going to give you a quick general overview of roughly how it works, just to give you an idea. It's something that I wish someone had told me before I started looking into it, because it didn't really become clear until the end what was actually going on. So what I did was I picked, I think, something like 3 different tutorial videos on the RedBlackTree, and I think at least 2 of them were from university lectures I found online. So, everyone seems to be giving a RedBlackTree discussion online, but I would recommend trying to use university lectures because they're going to be the most robust. Because one of the videos I actually watched was very good, explained it really, really well, but in one of the cases in the algorithm it was actually incorrect, so I had to correct that. But the nice thing is about using a number of different sources, everyone explains it in a slightly different way. And once you've understood one, then go and watch someone else explain it and see if you understand that as well, because they'll be explaining it in a different way and you might think they've made a mistake, but they're not. They're just doing it in a slightly different order or slightly different algorithm. So it's always good whenever you're learning anything in life, I think, to have a number of different sources and then cross-reference them, make sure they're all pointing towards the same answer. So that's how I did it. Like I said, it took me a couple of days, I think, and it was fun. It was really nice to learn something new, and I definitely recommend trying it. It's, if you haven't done it at university, it's really worth looking at. Actually, before we go into the code, I was just so we've got something to stare at while I talk, a quick image. So what is a RedBlackTree? A really, really quick overview. Not going to go into any detail at all. But basically it's a binary tree. So you've got, each node has 2 children and the left child is less than the parent child and the right child is more than the parent child. So that's, at its very simplest, that's a binary tree. Why is it called RedBlackTree? Well, some nodes are what's called coloured black and some are coloured red. Now all this is a bool in each node, which is set or not set. So it's nothing to do with colours or red or black or anything, it's just a bool. And the reason that's done is there are certain constraints which you have to keep when you're adding and removing items to this tree to keep it balanced. And the red-black bool just makes it easier to check when you've got a case that violates those rules, and then you have to do some fix-up to make it to keep it balanced. So they're just a helper for the algorithm. The red-black ball is just a helper for the algorithm to use so that it knows how to balance a tree. And I'll come on to balancing in a minute, but basically you can, when you add things, you can recolor them or you can rotate them, which I'll come on to in a minute. And so what do I mean by balanced tree? So let's imagine we just have the root node. So we're starting a new tree, we just added a node, it just goes at the root, that's fine. And then we add another node, 5, where does that go? Okay, let's parent it to the root node, why not? And this is still a balanced tree. But what happens if we do this? We add 1. Okay, so our algorithm goes, okay, let's find where it is. It's less than 5, so it must go to the left of 5. That's okay, but now it's not a balanced tree because we've got all the nodes on one side and nothing on the other side. So we have to rebalance it. And the main way we do that is through a rotation. And what we mean by rotation is, at the moment we've got 15 as the roots, and then 5 and 1 come off that as children. We could easily make 5 the roots. So what we do is, let's just launch my pen. No, not Epic Launcher, Epic Pen. I like the way you can't quit Epic Launcher. It's a nice feature. So, let's see if this works. So, number 5 becomes the root, and number 15 goes down here, and then number 1 moves up. So this is why it's called a rotation, because it's rotating the whole thing around, so we give number 5 the root instead. And after we've done that, obviously it's a balanced tree, which is great. That's what we want. We've got a root and then the same number on this side and this side. And like I said, the red-black Boolean flag, in this case, there are certain rules you have to abide by. And I think one of them is you're not allowed 2 reds in a row. Okay, so here we know it's not balanced because we've got 2 reds in a row. And after we do the rotation, we have to do a recoloring. And we recolor the root. The root is always black, that's the rule, and then the children are red. And it may seem a bit arbitrary, the recoloring, but there are rules about when you recolor, and I think it's always after a rotation or something, you then do a specific recolor, not just any random recolor. You have to do a specific recolor, and then you have a tree which follows the rules, conditions that the tree must always hold. And there are a number of cases. I think there are something like 6 cases for insertion when you're adding a node, and 6 cases for a removal. So whenever you add a node, you have to do this rebalancing, which is a set of rotations and recolorings. And then at the end, you end up with a nice balanced tree. So going back to our example tree, this is a balanced tree. As you can see, it's not all coming down one side. And as you can see, there are no 2 reds next to each other. So that's how we know it's balanced. And if we were to add something, say down here, after 23, if we add 25, then it would suddenly become unbalanced. And you can obviously just see it's unbalanced for that. And then we would do a series of rotations and then recolorings to get it back to a balanced state. So that's basically the idea. what else was I going to say? Yeah, sometimes we have to do multiple rotations. So as the tree gets bigger and bigger, you'll do one rotation to fix up a small area, and then you'll have to do another rotation further up the parent, and then maybe another rotation further up. And that can get fairly expensive. But it's never going to be more than the height of the tree, which is why it's logN complexity. So you can be guaranteed that it's not going to get past a worst case, which is really nice. I think if there's anything else to say on that before I go on. So why use RedBlackTrees at all? Or why use the map? Why use a map class? So I just call it my map, which uses RedBlackTree internally, which is the same as std map, as far as I'm aware. And as I was saying last week, hash maps are incredibly fast, especially the one that I talked about. So why would I ever use a map? And that's a really good question. And basically, it's I'll use it when I don't care about performance that much. And so let's just note them down. So that's the first one. I don't care so much about perf. It's not going to have thousands of entries, and it's not going to be adding, removing that much. Maybe it's only got, say, 100 entries or less, or even 10 or entries or something like that. The other is you don't have to write a hash function. So writing a hash function is hard. It's really hard to write a very good hash function. And as I explained last week, if you don't have a good hash function, you can have really terrible performance in a hash map. The hash map really depends with its performance on how good your hash function is. And sometimes you just don't want to write a hash function. If you've got a key, which is a complex struct with lots of members, etc., you probably don't want to write a hash or research how to make it really, really good hash. So you just have to write a less than operator and an equals operator. And so it's very easy to write those two things usually, much easier than writing a hash. So that's when I would use a map instead of a hash. And related to that, it's got bounded performance. So as I said, the hash map, if you've got a bad hash function, you can get absolutely terrible performance because all values get hashed to the same value, and then you get collision on every single one. It's no better than iterating through a huge array. So the nice thing about map is that we know it's logN perf always. So all you have to do is write these two operators, and then it's logN. And it's never, ever going to be worse than logN. And that's a really powerful thing to know. You don't care about perf, but you still don't want it to be terrible, okay? And it's never going to get worse than a certain complexity. And so you can kind of rely on it. It's kind of the bog standard thing I'll use if I've just got a small number of things in the map, say less than 100 or something. I don't want to write a hash function because I've got a complex key operator, or I'm just too lazy or whatever, or it just doesn't matter for perf. And I know it's going to be bounded performance. It's never going to be terrible. Like a hash map can be terrible sometimes, but a map will never be terrible. And it also uses up less memory than at least less memory than the hash map I described last week. So I have two maps that I use for pretty much everything in my code. I either use a hash map or I use one of these RedBlackTree map classes. So those are the reasons why you might use a map instead of a hash map. And I'll go through some examples in my code in a bit and show you where I've used them and perhaps why I've used them. So going to the implementation, it's only about 700 lines of code, and it's not actually that much. For a complex algorithm like this, it's not a lot of code. So once you understand the algorithm and you know all the 6 insert cases and the 6 deletion cases, it's just a matter of coding them up. And you know, there are so many implementations and pseudo algorithms on the internet and video tutorials. Like I said, it's kind of very easy once you get the idea of what's going on. And it's not a lot of code, so anyone could write this in a day or two easily. So let's have a look at the code. Okay, right. So this is my RedBlackTree, and actually, let's look at the map class. So my map container is a key value template, a template with a key value pair, and internally it just uses a RedBlackTree. So the reason I separate this off because I might want other containers to use my RedBlackTree. So that's quite a nice thing. RedBlackTree is a very specific, well understood thing. So you don't want to start messing about with it and putting it directly into your container class. Because I've got a set class as well, which again just internally uses the RedBlackTree. So, and obviously the node in this case is a pair because it's got a key and a value, whereas in the set it's just a key. So it's nice to do that. It's nice to abstract out the RedBlackTree to its own thing, and then you can use it in whatever container you like. So each node, oh yeah, here we go. Here's an optimization. So each node obviously has a parent and 2 children, which is fair enough, just node pointers, and the value. Okay, so it also has a red-black flag to say whether it's red or black, and I've inserted that into the parent pointer. So as you know, pointers don't use all the bits, so I've just used the lowest bit here to say whether it's red or black, which is, you know, if you've got a map with like hundreds or maybe even thousands of entries, it does add up having an extra ball here because that will add, you know, probably extra 16 bytes to the struct once it's aligned. So stuffing that one bit into the parent pointer is a nice little optimization. It's not a huge deal, but you know, it might as well be done. And then just load of getters and setters. Nothing that interesting. So let's go down to the bottom and see what members the RedBlackTree has. So it has the root, obviously, node pointer, and there's just a count and a node count. I can't remember why I added a separate node count. Yeah, I think it's just... one thing I didn't mention in this is that each node has 2 null nodes on it, or at least, you know, each node has to have 2 children, and they're called null nodes, and they need to be there and they need to be coloured for the algorithm to work. So that's one thing you've got to keep in mind. There will be more nodes than the things you've added. So it would look something like that, where these yellow ones are null nodes. So I think that's why I added a separate node count, but I can't remember where I actually use it. So it's just allocating and freeing a node. How strange. It's not actually used for anything useful. So I can remove that. That's nice. Save a bit of memory. Let's just check it's not used anywhere else. Nope. Nope, I can remove that. It's probably for some statistics or something. Okay, so anyway, root node, account, and an allocator. I'll speak about that in a minute. But anyway, it just allocates nodes, the class I just showed you at the top. And it's nice to have an allocator, because I mean, like the SDL classes, for example, won't have an allocator by default. You can obviously give them one, but if you don't give them one, it will just allocate off the main heap. And why would you ever not want an allocator, is my reasoning. If you've got a reasonably good allocator, why would you ever not want to allocate from an allocator and have all the memory contiguous next to each other and nice and fast and cache friendly? So anyway, let's take a very quick look. I'm not going to go through all of this code because, like I said, it is very complicated, but it's just implementing the algorithms which are, all over the internet. So you don't need me to go through that again. So let's take a look at contains. So we're looking up the value. Is this value in a tree? Start at the roots, and then while you don't have one of those null nodes that I talked about, if it's less than, if the thing I'm looking for is less than the root node, go to the left. If it's more, go to the right. And if it's equal, then we've got it and we return true. So it's very, very simple to look something up, because you know it's balanced and you know that each child, the left child is always less and the right child is always more. It's very easy to look it up. You just walk down the tree, and obviously it's logN, the height of the tree. It's bounded by the height of the tree, which is logN. So, really, really simple. A little optimization here that's worth doing, I think, is the order of these, because you might think, I'll check left first and then check right and then check as equal, or the other way around, you might check equal first and then check left and then check right. And it's a little bit more optimal to check the less than first, because it's more common than the equals case. So if you've got a big tree and you're looking for something, you're probably going to have to iterate a few times. So you'll be checking the left and right child more often than you will be the equals. So we know if it's less, we can go there. We don't have to check the equals first. So we don't want to check the equals first. And we could do these in either order, but I think there was a reason I did the equals before the right child. I can't remember what it was now. It might not matter. You might be able to do those two in either order. So question, how do I pack the red flag? I think I talked about that. Well, I can show you exactly how I pack it. It's just ORing it into the pointer. So I've got a set packed pointer function, which I use, was just general function I use for lots of different things. And it just does that basically. So it casts it, it's assuming obviously a 64-bit, and we got a 64-bit pointer. And it's literally just ORing it in. And that's all it does. And then I've obviously got a get packed pointer bit, which just ands 1 and says is the bottom bit 1 or 0. So these are nice functions to have just in general for everything if you do want to pack stuff into pointers. So obviously be very careful with it. And because pointers are always aligned in 64-bit to 16 bytes, then you've got quite a few bits you can always play with. Some people use the top bits, but that's dangerous because you really don't know how many top bits you're going to use, the pointer's going to use. It's not, I think it is well defined. You've got a number of bits at the top you can use, but I just prefer not to rely on it from the 32-bit days when it was using all the bits in the pointer. It is safer to use the bottom bit because that's never going to be used. You're never going to have a pointer to an odd memory address. So you can always use the bottom bit at least. So anyway, that's how I pack pointer. Another question, did you use recursive algorithm in the tree? No, I didn't. So I didn't use recursion. Well, I don't think it's really needed actually. I don't think any of our algorithms require recursion. And also I tend to avoid recursion in general because it's usually not the fastest way of doing it. I mean, there is a proof that shows that any recursive algorithm can be reorganized into a non-recursive algorithm, and at least in my experience, it will almost always be faster to use the non-recursion method. But recursion is useful sometimes because it makes things much simpler to implement. So yeah, no recursion. And go back to the contains. Yeah, I think we covered that. So yeah, it's pretty simple. You can't get more simple than that. Now I have actually repeated that algorithm a number of times, like say, for example, the get value. So actually, that's not a good example. Let's try get value. Let's look at when I've repeated it. I mean, I could have factored it out. I'm not quite sure why I didn't. I think I was just paranoid about inlining and stuff. Sometimes with some compilers, if you have too deep a call stack, one function calling another function calling another function, etc., sometimes you don't get inlining. So I think I was just being paranoid about that. And it's only a few lines of code, so I decided to duplicate it. But other than that, it's just the same. You just need to add a local stack and you don't need to recurse. Yeah, pretty much you can usually get around recursion by using a stack instead, which is a really good thing to remember in general. But sometimes it does make the algorithm a whole lot more complex to not use recursion. So I've got a clear and leak. For most of my containers, I've got a clear and leak function, just so that when I shut down the app totally, I don't need to go and deallocate every single node in the thing because it's just slow. So I just tell the allocator to chuck it away and not care, and the OS will clean it up. Clear, insert, remove. Let's look at insert first. So find insert node just goes down and finds the node just like we saw in the contains, using the same algorithm again. But if it doesn't find it, it allocates a new node. So that's the case where it's already in the tree and we're just replacing the value. So we found one that is identical and we just replace it. Now, so this is setting the red flag on it. So any new node you add, you automatically assign it as red, and then you do the fix up. So that's all the rotations I was talking about and the recoloring and stuff like that. So this is ensuring it's a balanced tree still. And that's where all the sort of complicated stuff happens for inserting. And I think I said there were 6 cases, and you can just look them up and then code them from pseudo algorithms you can find. I'm not going to go through all of these, but basically they're just checking the parents and the uncle node, I think it is. They're checking what colors they are and then deciding what to do, whether to do a rotation or a recoloring or whatever. And like I said, this is a while loop, so it doesn't need to be recursive. And then these are just other cases. So we've got a second case here where we're doing a rotate left, and we've got the third case there where we're doing a rotate right. So we might need to do both. We might need to do a rotate left and a recolor and rotate right here. So it is a complex algorithm, but it's kind of so well understood now that you just got to code it up really. Oh no, case 2 and case 3 again. So again, just different rotations. And that's it for the insert. So it's not a huge amount. And don't forget these rotations, when we're doing these rotations, like after that, we rotate to that, we're just fixing up pointers, basically. We're not doing any copying of the actual node's keys or values or anything like that. We're just swapping around pointers, so it's not as expensive as you might think. And most inserts only require 1 or maybe 2 rotates and a few recolorings, which are just setting a few bits. So it's not as bad as you might think. And then we've got the remove somewhere, where I've put the cases in the actual remove function. So again, we've got a load of cases of what to do when we remove. It's a little bit more complex on the removing, so keep that in mind. And again, it's just checking the red-black flags and then doing rotations. And this is just going through all the different cases, and there are like 6 in total, I think. And the last case, it's so complex, I've actually added another function for it. I think it's if you end up with 2 blacks in a row or something like that. And then for that last case, there are a number of subcases you need to do. And there are 6 cases in that. So yeah, I'm not going to go through that. I don't think there's anything worth pointing out. It's pretty... Oh, I used to go to here. I think this is the only go-to in my whole code base. And to be honest, I really didn't need to use a go-to. I could have just inserted that here instead and duplicated the code. But anyway, why not? Just for the hell of it, let's use a go-to. And that's it. And like I said, it's only about 700 lines of code in total, so it's not a huge amount of code. Actually 900 lines here, but most of that is for the iterators. So basically just got an iterator, you just pass in a tree, it stores the current node, and then the increment just goes to the next child or goes to the leaf, etc. So it's just a standard walk of I think it's breadth first walk. It might be depth, I can't remember. Anyway, it's pretty standard iterator. And I didn't use a range-based iterator. I really must change that. Everywhere in my code, I'm still using my old style iterator. And it's really annoying. I really need to change that to a range-based iterator. So I can use a nice range-based for. So, unless anyone's got any questions on that, I don't think... Oh yeah, the checking functions. When you're writing it, I would say you must write some checks for the tree, because like I said, the whole RedBlackTree algorithm is based around a set of preconditions that you must be kept. So like you can't have 2 red nodes in a row or things like that. And it's very easy obviously to make a mistake when you're coding the algorithm, so just write yourself a quick test function which tests all these conditions that the tree needs to always meet. So after every insert or remove, just check the tree still holds those conditions, and then that'll make it so much easier to detect any bugs. Okay. Just to get memory usage function there is always useful. Oh yeah, I said I'd mention the allocator. So this allocator is what I call a growable fixed size allocator. So for me, a fixed size allocator without the growable part, a fixed size allocator is just, it allocates a block of memory, say 4K or whatever, and then chops that up into lots of slots the right size, and then you just have an alloc free list from that. Which is fine, but when you've got map classes which are really small, you don't want to allocate a whole 4K page. So what I do is I grow the allocator. I start off with something like 32 entries in this allocator, and then I allocate another chunk of memory of 64 entries, and then I allocate another chunk of memory of 128. And then, so each time I'm allocating a chunk of memory, I divide it up into slots, which I can then put on the free list. So the memory growth of this is the same pattern as you would have in an array class. So it's growing in multiples of 2 each time. And that kind of is a good halfway house between allocating a huge chunk of memory and then never having to do it again, and allocating every single node in isolation off the global heap. So it's kind of halfway between the two. And it works quite well. You know, as the class grows, you'll have fewer and fewer allocations, and you won't be fragging memory, and it'll be much more cache friendly. But obviously, as with any container, like I was saying last week in the hash maps, you do need to reserve as much as you can. So if you reserve a whole, say you've got 1,000 things you want to add to the map, if you reserve 1,000 first, it'll reserve out of this allocator, and it'll say, okay, allocate as much memory as you need, like pages of memory in one single allocation that's enough to hold 1,000 elements. So if you reserve first, it'll only do one allocation and then never allocate again from the global heap. It'll just come from the allocator. Yeah, so it's not contiguous. It's not guaranteed to be contiguous. But you imagine if you've got a map which is growing from one element up to 1,000 elements. By the time you get to 1,000 elements, the majority of elements will be contiguous. It'll only be like sort of smaller elements that will be individually allocated. So, you know, you add the first node to the map, it'll just allocate one single node, or actually I think it's 32 lower bound, so it'll allocate 32 nodes on the first allocate. And then I'll allocate 64 nodes on second allocate. So those won't be contiguous. But that doesn't matter too much, because as the map gets bigger and bigger, it's more likely to be contiguous. And if it's a small map, you probably don't care about cache hits anyway. And like I said, if it's something really big map, you just reserve it first, and then it will be contiguous. So hopefully that makes sense. And I've used that quite a few places in my other container classes, and I think it's a really nice sort of compromise between the two ways of allocating. Okay, so that's class. So let me know if you've got any questions on that. Yeah, so let's go back to my notes. I was going to show just a few examples in 10x, and then I'll talk a little bit about my WStringHashMap class, and then I think we'll call it a night. Brian, yeah, since the use case for smaller numbers going to a hash map, have you considered using indices rather than pointers? Let me just check I've understood that. Here's what I think it is. Yeah, I mean, I think you're saying actually what I was thinking about earlier today when I was thinking about this, that instead of using pointers, we could use indices into, say, an array. So we could change this to just a standard array, and then these pointers would be indices into that. And that would be nice because it would keep everything contiguous. So when you if this was an array, say, oops, can't type. So we could do something like that. So instead of using an allocator, we just use an array, and then we change these pointers into indices into that array. I think that's what you mean. If it's not, let me know. And one reason that's slightly nicer is all the objects will be contiguous in memory, so it'll be more cache friendly. And the nodes will be smaller, because remember each node stores a parent and two children, so they would just be indices. So the node would be a lot smaller, and it'll all be contiguous in memory. The downside of using an array as an allocator, obviously, is when you resize this, you're going to be doing a lot of copying of the keys and values of the nodes. And for me, the copying is probably the killer. I wouldn't do it that way. But it's an interesting. I was thinking about it earlier, and it's an interesting thing. Might be worth trying one day to see if that is actually better. Yeah, so large cost reallocating being the downside, and yeah, it's debatable. I think it probably would be similar. Might be slightly faster in some ways because the node would be smaller, and when you're iterating over contiguous memory, and it'd be less jumping around in memory very slightly. So it might be better, but I think for me the copy. I mean, imagine if you got thousands of elements in this, the copy would be really substantial potentially. I like to put quite expensive values into my maps sometimes, and I wouldn't want that hidden cost of occasionally having a really big spike. But like I said, I only usually use my map classes for smaller values, so it probably wouldn't make a huge amount of difference. But I don't like having a really bad worst case spike in it. So that's the reason I prefer to use growable allocator and then pointers. But yeah, it's an interesting thing to think about. So I was going to show you a few examples of where I use map. File packages. It's weird. Okay. So yeah, this is my package system where I have, like in 10x, you'll see this is a 10x.data file, which is all the files packaged into one file, and this is a list of packages. Now in 10x, I only use one package, and even in a lot of games I worked on, you don't have, that many packages, maybe tens or so, or maybe probably less than 100 or so. So this is the case where I've just used a map. The int is a handle to the package, and then you've got the package pointer. So there aren't going to be that many of them ever, especially in 10x. So I've just stuck with a map there. And the main reason probably here is because it will use up less memory than one of my HashMap classes. Because it wouldn't be hard. I wouldn't have to write a hash function for my handle here, because I can just pass that. As I said last week, I can just pass in ints to my HashMap class, and it automatically creates a hash out of that. So I wouldn't have to write a hash function here. So mainly it's just memory. But I could easily replace that with a hash. There's no big deal either way in that case. Let's see if I can find another. See if I can find a good one. Yeah, I mean, I'll use them with string keys, which isn't very efficient. But that was before I wrote my WStringHashMap class, which I'll mention briefly in a minute. Yeah, pretty much all of them are string. Oh, it's not going to work. That should have worked. I think I need int10x at the end. Nope. Oh, anyway. I'm trying to find a good one, yeah, where I don't want to write a hash. Okay, what's this? 10x main, puzzle files and directory. So this is just getting a list of the files. Anyway, whatever this is doing, which I can't exactly remember what. It's basically just getting a list of files per parser factory. So this is for when I have multiple parsers, which I don't have yet. For when I support other languages like C# and Python, etc., I'll have a parser, for each language. And regardless of what this is, it doesn't really matter. I don't really want to be writing a hash function for a pointer. I've got one somewhere, I think. Yeah, I definitely know I've got one somewhere. But I'd rather not. It's a bit messy, and hashing pointers is always a little bit tricky. It's a bit fiddly. You don't always get great results. And there are never going to be that many. I'm never going to support thousands of languages in 10x. I can guarantee that. So there aren't going to be many things in this map. I don't want to write a hash function. I don't care about memory in this case. So I'll just use a map class. But you get the idea. Just those things I talked about. I don't care too much about perf because I'm not going to have that many. Can't be bothered to write a hash function, or just too lazy, or just it's too awkward to. I know it's never going to be terrible perf, even if I do suddenly start adding tens more languages to 10x, and I know it's not going to use a ton of memory. So those are the reasons I might use the map. So moving on. I said I'd briefly mention WStringHashMap. I don't know if I won't talk about it today. Maybe I'll talk about that another time. But just to explain why I added it. Actually, yeah, this is probably I could talk a whole half hour on this essentially. But anyway, as you saw, a lot of places in the code I'm using maps with strings. And obviously that can be a problem for performance. So what I wanted was just a nice, easy hash map I could use, where I didn't have to bother writing any hash functions or anything, and it would deal with that all automatically. So I just decided to write a dedicated HashMap class specifically for strings as keys, because I'm using strings obviously all over the place in 10x and in the parser. And that turned out to be a big win in lots of places. And I'll talk about it more another time, but the nice thing about WStringHashMap is it goes to great lengths to not copy strings around if it doesn't have to. So when you're looking up a key in a HashMap class, you don't want to be passing in a key and then copying that key and looking it up and comparing and stuff. It's difficult to explain, but it basically avoids lots of string copies everywhere. So it's more efficient than just using a hash map and using string as a key. But I'll go into that another time, I think, because that's a whole big topic in itself. Yeah, Brian's saying it'd be interesting to have a test class which uses HashMap and RedBlack to compare perf. I mean, really, there's not going to be any comparison. HashMap, assuming you've got a good hash function, will always beat a map class hands down without, there'll be an order of magnitude speed, increase in the HashMap. Because if you look at the lookup, which is get item index, assuming you've already got the hash pre-calculated, which you would most of the time, and assuming you've got a good hash function, like I said last week, so you've got a sparse array, you will literally it's just a mask, and you're there, you've got the index. So it's like two operations. You cannot beat a hash map that's performing well ever. So I always know a RedBlackTree map will always be slower. So like I said, I'll only use it when I don't care about performance. If it's only got a few items in or it's not used heavily and I just can't be asked, I'll just stick a map in and be done with it. But I know it's never going to perform well as a hash map. And as I've been working on 10x, I've a lot of the time started off with a map class, and then as I profile and start noticing, oh, that map is being hit a lot, or it's grown in size from what I expected, then I'll just go through and replace it with a hash map. And I can pretty much do that without hardly any changes, apart from writing the hash function, of course. But you know, the function names are standard enough that my map class, you know, add, remove, contains, etc. They're standard enough and operators that I can just swap one for another without really any work at all. So yeah, that's kind of my thinking of when to use one and another. And like I said, I pretty much use those two everywhere. I have got a few other what I call hybrid maps, which I might talk about another time, but they're not used very often. You know, like I said, I use a map or I use a hash map that I described last week, and those are the workhorses of my entire code base. It's what I use pretty much everywhere. Okay, so we've got a few things I could talk about next time. Like I said, I could talk about the string hash map, the hybrid maps, which aren't as exciting as they sound. Maybe other containers as well. But I'll have a look through and see what I think would be the most interesting to go through. So anyway, my brain held up more than I expected, and I've been going for 50 minutes. So that's pretty good. So I think I better call it a night there. And I hope you found that helpful. And I really recommend go away and write your own RedBlackTree. It's fun. Really, seriously, it's good to learn new stuff, and pretty much every programmer I think should at some point write one. You probably, if you've been to university or whatever, you've probably written one anyway. But if you haven't, it's well worth doing. It's not as hard as it might seem. So anyway, I think I'll leave it there, and I'll see you next week. So take care and bye for now.